get started. So we have to have the Jiakang from IPMA. So he's gonna tell us 2, 3, 4 of crystal method. Please.
Thanks. Thanks for organizing this wonderful workshop and thanks for having me here. There are many experts here, and you might find what I'm going to talk about quite trivial. And it's the first talk after lunch, so it's a good chance to take a nap. Anyway, so I first need to explain what what this funky title of the talk means. So especially these 2, 3, 4. So I'm going to talk about crystal melting. So at least for Turk carbonyl threefolds, it's a well-known story that this crystal melting model encodes the BPS spectrum. Right, so this crystal is actually 3D, so maybe I can make those. So we have this 3D crystal, and this is sort of like a one-dimensional uplift of the periodic quiver, which lives on T2. And this quiver originates from brains probing the Turk carbonyl threefold, so it's like from 40 n equal to 1 quiver. From like 30 years ago, we always believed that these BPS states have some algebra structure, and in this case, we'll talk about this is something called Quiver-Ionians, and it has 2 parameters, so this is another tutor. And I'm also going to talk about Turk carbonyl fourfolds, but from a different setting compared to the talks this morning. So here, well, naturally, we'll get this fourfold, this is threefold, so naturally we'll guess, okay, we should have some 4D crystal, which sort of should give us some tell us how many BPS states at each level, but well, we'll see. Indeed, we do have these crystals labeling the fixed points, but somehow, if we write down the BPS index, there are some non-trivial weights. And of course, so here, we should write the quivers are 2D n equal to 0.2 quivers, whose periodic quiver lives on the 3 torus. And of course, then we'd wonder what algebra should we have? And from this table, a natural guess would be some algebras with 3 parameters. But I should put a question mark here because we still don't know what this algebra looks like. And yeah, I also mentioned some difficulties in this construction. So I'll talk about so basically our settings type 2A in these Turk 3 and 4 folds, and so I'm not gonna go to the A side as what we learned from Mauricio yesterday, so I'll just do something we know from kindergarten, which is so D6, D4, D2, D0 random states, where this D6 is non-compact, so this serves as the flavor ring. And here for 4 folds, we have something slightly different. So we have a pair of D8, D8 bar, which are non-compact. The reason, well, of course we can just consider this D8 without this anti-brain. But here we are writing this. One reason that if we, when we write down the quiver, we would have, so this is the flavor of the framing, then we would have both the Cairo and the Fermi. Well, the Fermi is expected to come from the anti-brains. And if we consider this d8 bar annihilated to a single d6, x4 cannot be a 3 times c geometry, we should recover this BPS partition function for the torque threefold case. If we just take some limits of the like fugacities, the parameters of the case here. So yeah, so I also need to talk about the quivers. So well, we know what the data we have in the quiver. So like we have this round node, which denotes the gauge node, and we also have the square, which I've already drawn there, which is the framing or the flavor, and then we have arrows, which denotes the but if we have two nodes, then it's the bar fundamental. Here it's just fundamental of this gauge node, and of course I can have like say self roots, which transform as the adjoint. So here this is the C3 quiver, and for fourfolds, because we are in the 0,2 language, so we have besides like okay, I can have like four arrows here, and I can also have these non-oriented these edges without orientation, because we also have Fermi multiplets here, and because in our Lagrangian we can just have this, the Fermis and their conjugate are just symmetric, so these multiplets in the quiver they don't have orientation. So this is like the C3 and this is like the C4 quiver, which well, this one just can be directly obtained from this using dimensional reduction, and we just decompose the 2 into the 0,2 language. So I was mentioning, so of course by quivers I always mean quivers with relations. So of course we know for like the torque threefold case, we have superpotential and we take the derivative, we have the F term relations. Like for that case we just have 3 arrows. Well, this is one node, so we just have well, maybe for example x1, x2, x2, x1, and of course we have the other 2. And for fourfolds we have J and E term relations, and because this is toric, and from papers by Franco, Song, and other people, we know that these J and E terms they can be written as in this form. So here, maybe I should and this JBA plus minus and EAB plus minus, they're just monomials of the Kairos. For example, for this C4, we'll have 3 Fermis. So let me just call them lambda 1, lambda 2, lambda 3, and we'll have these J and E terms. Well, if we just label the Kairos by x, y, z, maybe W, maybe I shouldn't use W, maybe let's use D. Then this is like xy minus y x. This is like dz minus zd, and of course we have xz minus zx, dy minus yd, and these are similar. So you might also find like here we have, I kind of like use different ways to write the subscripts. These are like BA, these are like AB, because when we draw the periodic quiver, which is like it's a 3D quiver. By 3D quiver, I mean it's on the 3 torus, but it's like 2D quiver. So when we draw the periodic quiver, these 4 terms they are encoded by the so-called plackets of the quiver. Namely, they are faces surrounded, like enclosed by 1 Fermi and these Kairos. So for example, if I have a something like this, I have B and A, and I have a Fermi, then I can have, for example, something like this. Because it's going, maybe I should, yeah, maybe I should. So this is like J, because it goes from B to A, so we'll have JBA plus, and then I have another packet which looks like maybe something like this. So this is JBA minus, and for this Fermi, I would also have another DE terms. So it doesn't have to always to be like triangles. It can have multiple different numbers of the chiros. So maybe I can have something like this. Or maybe this is EBA plus, and I can have something like this. This would be EBA minus, and in the quiver I just put them together, so it will look like that. So it's very hard to draw, but we'll have something like this. And then I would have a well, it's very hard to draw these 3D diagrams, but you know what roughly looks. So it's kind of like you have a Fermi in the middle, then I have like a crossing of the 4 plackets, like these 4 plackets. They just give me they just tell me like what the J terms and E terms look like. And so now we have the quiver, and we want to uplift to the crystals. So as I was saying, these are like 4-dimensional, well, 1-dimensional uplift of the periodic quiver, where the extra direction is sort of given by the R-charge direction. Right, so roughly speaking, I mean, just like schematically, I have some crystal, and what we learn from like torque threefolds, we know that like at each different configuration of the crystal give me like different BPS states. So if I have a quiver, so suppose I have a quiver which I pick some starting reference node in the quiver, which corresponds to like the initial atom in the crystal. So I can just go along some random path in the periodic quiver. So I would just reach another node in the quiver, and this path maybe I should call it P. And because of these relations, either the F term relations or the J and E term relations, I can always write this as V omega n, where V is this shortest path, and then this omega is just a loop. So I can just going this path is equivalent to going this shortest path and then going this loop n times. So in the crystal, I just have this V sort of along the surface of the crystal. So if it's 3D crystal, then it's just literally surface. Then if it's 4D crystal, then it's sort of like the 3D surface of the crystal, and I just get this atom, which corresponds to this node in the periodic quiver, which lives at depth 0, and this going this loop n times means I just go depth n. So I would have the corresponding atom for this path. And of course, because we're saying like we're melting the crystal, so we need to satisfy some rules, which is called the melting rule. So again, melting rule. So we say I is I dot A is in the crystal, maybe I just call it C. where A is some node or some atom in the crystal, and I is a chiral and iral whenever A is in the crystal. And well, this is going to say A is not in the crystal whenever I dot A is not in the crystal whenever A is not in the crystal, and this is equivalent to say A is in the crystal whenever I dot A is in the crystal. And if you like path algebra, this is equivalent to say that this path algebra is CQ, and I model out the relations depending on the 3-fold and 4-fold. This means the complement of the crystal is an ideal of this Jacobi algebra. Well, I guess it's quite trivial to say this rule, but it does rule out all the configurations that we don't want. So, for example, I mean, just like a very simple example, we have this initial atom. If we just like focus on, like, say, the 2D surface, I first initial atom, then I can just add one here, which is fine. But I can't add one here. Well, suppose this is like C3 or C4 case, which is given by plane partition or solid partitions. Then this is not allowed. Well, because I have this thing here. This one is not present, which says, so if I call this shaded one A and this arrow going from this to this I, then this is I dot A. So this should not be in the crystal because this one is not in the crystal. In other words, this should be in the crystal because, well, suppose I have this configuration, then this is in the crystal, so I must have this one in the crystal. So basically that's how we rule out these unwanted configurations. So I've been talking about crystals, but I still haven't verified that we do have a crystal. Well, I mean, for 3-fold it's like a well-known story, but for 4-fold it's just our like hope. But we still need to justify our statement. So one way is, well, because we're actually like counting the BPS states, so to see this like crystal structure is just to compute the index. And we know from like Benini, Eager, Holly, Chicago, and also some following up papers, we know we can use the JK residue method to compute the crystals, to compute the index. And then from the poles of the JK residues, we can actually tell that we do have this kind of crystal structure. So, well, I guess I don't have to really introduce all the notations here. So I'll just write down well, the formula just as in just for completeness, but I guess we all know what this means, but and yeah. So here we always choose this eta to be 1111, the diagonal 1111, because it gave a, well, so we're focusing on the sort of cyclic chamber, which has some, well, because it has a nice crystal structure. But I think I do need to write down the one determinant, the expressions for the one determinant, because I actually want to do some like very simple calculations. So for vector multiplet, which transforms as the in the joint wrap, so I just write the rational version because we just want to find the structure of the poles. So we can just each gauge node I have this expression where this epsilon I define it as epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4, which corresponds to, well, if it's fourfold, I have epsilon 4. If it's threefold, then just have up to 3, which corresponds to the U1 isometry subhalf. And of course, because it's toric cardinal 3 or 4 folds, in the end I need to take this to 0. So these frequencies satisfy this condition. And I also have the chiros. Okay, this is for threefold. Yeah, sure. Here, this Fi just denotes the weight associated to the chiral. If I have this thing, the weight is Fi, which is expressed in terms of these epsilons. And if I have the self loop, which are the adjoint chirals, I would have something like this. So why would I bother writing down these expressions? I mean, you can always find it in any literature discussing this. Well, one reason is that if we look at these expressions, everything is paired. Namely, the numerator, like for every expression, each factor has basically the same numerator and the denominator. So here, because remember, eventually we want epsilon to 0, so this is, well, if I just take epsilon to 0 here, this is the same as this is the same as this is the same as this. So everything is just trivial. So in the end, I would just get 1. So this means we first need to evaluate the residue, and then we need to take epsilon to 0. Well, this sounds a bit, I don't know. At first I thought this is like, okay, this is some condition we'll have to follow. But it turns out this is actually good, because this means if we forget about this condition, we get the refining index for the threefold case. Well, this is sort of like we just added some extra U1 to the index, and we get some refinement. There were some discussions. Well, actually, this kind of refinement is actually already conjectured like 10 years ago in the paper by Kunkov and Nekrasov, saying that this should be the same as the motivic ones, which sort of tracks the spin information. Well, they were saying like this conjecture is proven in an upcoming paper by Malik, but that paper never shows. So I guess there were some relations, but I'm not sure about and I think they are the same, but yeah, we still don't know how exactly they are related. But anyway, the other thing about this numerator denominator pairs is that we can actually see that everything, if we compute this index, we compute the BPS partition function, everything is just plus minus 1. So we just have numbers at each level if we write down the partition function. So when we take the residue, we'll always, because all these are simple poles, so essentially if we pick up some poles corresponding to these terms, So just sort of like remove this denominator. Then you might wonder, okay, we have some like numerator left in the end, but then this is taken care of by this epsilon. Anyway, we can, because it's an index, so I was saying it's plus or minus 1, so it has signs, but using, well, from this expression, we can actually tell whether it's plus or minus. So, well, it's just some like simple math. So from the vector multiplet, I have this minus sign. So for each gauge node, which is of say rank ni, then I have this factor here. And the second part, this minus sign, doesn't matter because it's ijji, so it's n times n minus 1, so it's even. So I don't have the remaining part. And then for the bifundamental, I know I have ni and j for I not equal to j. And then for this thing here, I have another n. And again, the second part doesn't matter because it's ijji. Well, we know this is ni and, well, we know like n and n squared, well, they are, well, in a sort of, well, they are the same mod 2. So I can just write this as ni squared. Then I can just combine these two terms. And of course, we actually have a framing to the rest part of the quiver. Well, this will be our initial atom because this is how we started to sort of grow the crystal. So of course I would have, well, if let's call this node 1, then I would of course have an extra factor like this. And this, okay, well, of course this is this sum plus this sum, because in the power of minus 1, so of course I can change this to minus. And this is actually the Euler-Lüger form. And this is exactly the expression for the signs of the Pipette states we have when we read the paper from Moscow and Renicky. So at least for threefold, we know, yes, we do recover the correct sign of the Pipette index. So that's threefold, and also we talk about fourfolds. Now we have this 0,2 expressions. Well, I guess I don't have to write down all the expressions, but well, roughly speaking, I have something like this. And for bifundamental, I'm not going to write down the expression, but it looks like something like this. And well, joint is roughly the same, so I'm not going to write. But then we also have Fermis. So this, maybe I should write down the expression. So I'm just assuming that this is just a bifundamental. I mean, for self-loop it's the same. So if this is n A, this is n B. Well, f lambda is still the weight of this Fermi, but now, but now I have something I have never introduced before, which is this T and S of lambda. Well, because we were saying like the Fermis are not oriented, but when we write down this formula, we still want something like, well, we still want this is maybe ij. So we still want like ui minus something like ui minus uj. So implicitly we're actually imposing some orientations to this edge, but we don't know how to well, if in the quiver it's just unoriented, like we don't know how to like actually put an orientation to this edge. Well, actually this is so mathematically there are also some papers defining this like DT4 invariance using like obstruction theories and well, I shouldn't go into the details, but there is also some like in the numerator of their expression there is some x2 and they have this kind of, because of surduality you can take the square root, and because of taking the square root you also have and like sort of choice of plus minus signing their like expressions when you compute the DT invariance. And well, I think there are mathematicians already know some of the like ways to actually some sort of canonical ways to choose the sum, but I guess yeah, I'm still not sure like if they still have like they have this paper submitted. But from a sort of physical way, we do have some ways to like fix this choice of T and S. So there will be no ambiguity when we write down this contribution from the Fermis. So here's an example for the so-called conical times C example. So if you like toric diagrams, so we know the conical has the toric diagram like this, which is just a square, and then conical times C is you just sort of uplift to a 3D polyhedron, which looks like this. Well, something like this. And the quiver, if you know we know what the conical looks like. It's just like this. Then, well, we can use dimensional reduction, and then we just get a quiver look that looks like this. So here, this big matrix is something called brick matching matrix. So this is kind of like some analog or like a sort of generalization of the brain tiling we know for Calabi-Yau threefold. So yeah, also let's maybe talk about like brain tiling. I mean, a brief recap. So this is like a brain tiling, which is also called the dynamo model, which is essentially a bipartite graph. So this is the simplest C3 case, and this is like the dual graph of the quiver, and the definition of the dynamo model is like the study of its perfect matching, which means I just choose I have a collection of the edges for this like brain tiling, and each node, either white or black because it's bipartite, each node is only connected or attached to exactly one edge of this collection. So for example, in this case I have three perfect matchings. But one is this. Well, because this is on T2, so these are like identified. And then I have this. And then I have the remaining one. So I have like three perfect matchings. So of course we can write down the perfect matching because this is like the dual graph of the brain tiling. So I know I have yes, I'm not sure if maybe I should go this way. Okay. So we know like each edge in the brain tiling is actually an edge in the quiver because it's dual graph. So we can always write down the perfect matching matrix, which tells me like this information. So for example, I have x, y, z in the rows corresponding to the three chiros, and I have say p1, p2, p3 corresponding to the three perfect matching. So if this chiro is in the perfect matching p1, then we just put 1, and it's not in p2, so it's 0, and not in p3. So here I just have a sort of like diagonal. So likewise, we can also have something similar for the Calabi-Yau fourfold. and this is called break matching. So this kind of three-dimensional generalization is called brick model. So it's not exactly the three-dimensional like diamonds, but instead it's something called brick model. So like for C4, well I cannot really draw this polyhedron here, but it's like some sort of dodecahedron which has 12 faces. So I have four rhombi and I have 6 hexagons, for example. So it's giving me like this polyhedron, and again it's a dual graph of the quiver on T3. So these faces actually correspond to the edges in the quiver. So for example, these are actually the Fermis, and these are actually the chiros. And then I can also define something similar to the perfectly matching, which are called brick matchings. Namely, for each in the brick matching for each Fermi, we were saying we have like sort of like 4 plackets, which corresponds to the J and E terms. Then I will only have the 2 E term plackets or the 2 J term plackets in the brick matching, and then this gives me this matrix. So these P's are and also S are the brick matchings, and these are the I only write down the chiros because once you determine the brick matchings for the chiros, the Fermis are automatically determined. So for example, these are this is like the collection of the edges for P1, and this is the collection of the edges for this S brick matching. So now, if I want to determine the weight of the Fermis, then I just need to pick one brick matching, any column, because eventually it will give me the same answer. So for example, if I have I choose P1, then I have X21, so I have X21, and then correspondingly I would have this here. But actually it doesn't matter, we just want to pick X21, so X21 is here, and X21 is here, and then likewise for the last one. Then, for example, for this one, I would just choose this thing here. So I will have so 1 and 2. Then I have roughly speaking, I have something like this. Then I want to, so this is the Fermi, but I want to close this loop or this bracket, so I will choose this direction. And then the weight of this Fermi would just be minus of the sum of the 3, or I mean here it's the same. So no matter which one I choose, it's always the same. So this, if this is like say epsilon 2 1 epsilon x21 epsilon x12 epsilon y21, then this is just minus the sum of the 3. And if I choose S, then I would have 511 here, and I would have 511 here, and also 511 here. So essentially, what I have is something like, because this is the J term, this is E term, they have like the opposite direction. So it's something like this. Then this Fermi, to close the loop, I sort of implicitly choose the orientation like this. So then, if we just look at this Fermi, these 2 brick matchings actually give me the opposite weights. But if we take all the 4 Fermis into account, eventually, okay, I have to erase the expression. The expression for the Fermi is it's always the same. It's always fixed, and there is like no ambiguity of like choosing the signs, etc. When we write down the index. Yeah, I shouldn't erase that, but there was another difference compared to the threefold case, because we were saying the threefold they are all paired, so eventually everything is just plus minus one. But here, if we just remember, like for chiros, we have something like this, and for Fermis, we have something like this. So things are not paired, which means I cannot, in the end, I would not get something like just plus or minus one. Instead, I would get something which is a like rational function of my fugacities, and in the so for example for the we know like the McMahon function, which is like the BPS partition function for C3 is like 1 plus Q, because I have one box at level 1, then I have three configurations at level 2, which are this one, this one, and this one, and etc. Well, we know like for okay, this is threefold, and for C4, this is like the solid partition, which is still like 1 plus Q, but plus 4Q, because I have like 4 directions, and but somehow this is not exactly, if we compute the JK residue, this is not the exact partition function, but instead I would have some non-trivial expressions which are rational functions of the epsilons. And this is the reason why I cannot just get simple numbers, because these are not, well, this is on the denominator, this is on the numerator, so they do not actually cancel everything. And there's, well, also I was saying, in this case, everything is paired, so if I just take epsilon to 0 before I value the residue, everything is trivial. I just get 1 and nothing else. But I was saying it's a good thing because I can have refinement. But here, I don't know how to write down the refinement, because we have to take this condition epsilon to 0 before evaluating. Although it doesn't, if we take this before evaluating the residue, nothing gets cancelled. Well, nothing like, we don't have like extra cancellations. But in fact, we do need to impose this condition before we evaluate the residue, because otherwise we would have some unwanted poles appear in this evaluation. We might even have double poles in the JQ residue. But if we just impose this condition already before the evaluation of the residue, then this means we don't know how to get any sort of refinement of the index. Right. So yeah.
So does the index you wrote on the right hand side index epsilon 1, epsilon 2, epsilon 3, and epsilon 4?
Sorry.
There are 4 epsilon parameters.
Yeah. So here it's only on this.
Oh. Okay.
Yeah, because I was saying like I want the 4-fold case.
And those it's calculate it's a generating function for the DT mark.
Yes, up to wall crossing. I mean, of course, I can also go to the DT chamber, but yeah, in general, I can get. So if I just have this thing here, then it's the non-commutative DT chamber, like like a different chamber of the DT mark.
So how do I read the DT mark from this generating function?
Sorry? Yeah. I mean, yeah. Okay. Yeah. You mean you want to read off the DT right from the generating function? Yeah. So. Yeah, we have wall crossing formula, so we just follow this wall crossing procedure, and we can reach the DT values. So now I want to talk about the algebra of the BPS space. first write down the relations of the, like defining relations of the algebras, but I guess it will be just better to write down the crystal as the representation of the algebra. So in the algebra we have three types of generators. So if I have a first type is called psi, which basically says your state is the your crystal as a state is the eigenstate of psi, where this current looks like this. So these psi n and also later E and Fn, they are my generators of the algebra. And then I also have En, which plays the role as the raising operator. Namely, I would just they just add atoms to the crystal. So roughly I have something like this. So here psi is this psi, which is just a function I'll write down later, and here this is the same. Well, f is like the lower ring, so it's like those remove. Well, it's essentially it's the similar expression, but this removes an atom from the crystal. And then if you okay, yeah, I should write down psi, and okay. And also, well, these are like n from zeros. And likewise for f, and this a is just a node in the quiver, because different nodes in the quiver corresponds to different like colors of the atom in the crystal, and then the relations will look like something like this. Oh yeah, and also write down psi. Psi is something look like something. So this C is not the crystal C. Somehow just do the scalar curly C, and then I have product of all. Essentially, some expression looks like this. So I have this kind of factor for each atom in the crystal, the C here. And then I also have this factor, because this is sort of like how I start to grow my crystal, because this Z looks at is the initial atom. So I will always put the initial atom in the crystal, say at Z equal to 0. So this pole corresponds to the position of this atom, and this C is some central element in this algebra. So for example, if it's a toric Cabriel threefold without any compact divisors, then this is just sum of psi 0. And if you like double algebra, then this algebra can be truncated to some double algebras, and this is actually go to capital L, where this double algebra is the rectangular double algebra JRM/n. Okay, yeah, just for we have this cover if you write down the mu operator is something like this. So just some little comments on the connections to vertex algebras. Anyway, the relation is just something looking like this. And I have a similar relation for f, but here it's phi minus 1. And then I also have this relation, the EF relation, which is something like this. So of course I have other relations like E and psi, F and psi and psi and psi, but they can be all derived from these three relations. And this sign here means it's up to some sporadic Zn, Wn terms in the mode expression. This is to ensure that for the mode relations there would be actual equality, but it's a bit too tedious and we don't write down the relations for the modes. But okay, there is a function here which is this phi, and this is sort of like a key function in the relation which looks like this. So here in the numerator I have the collections of all the arrows from A to B, and in the denominator I have all the collections of arrows from B to A, and these epsilon I corresponds to the weights of each arrow. And also I have this thing here, which is this A and B. This is like sort of a Z2 grading of this algebra. So a node we say is bosonical. It has gradient 0 if it has an odd number of roots, self roots. So this is node A, and I have an odd number. And otherwise, if I have an even number, then we say this has gradient 1. So basically that's the relation I have, and this factor is important not only because it gives the relation, but also it tells us like these are actually sort of the poles we have in the JQ residue. So they actually tells me where I can add the crystals, how I can grow the crystals, because here I have the residue of the psi, and the psi is basically the same as that expression. And here this plus epsilon is kind of like relations of the crystals, because it's kind of like here if I already have some crystal here, then I want to grow a crystal of color A from B, then they actually get disposed. And these are like these numerators are like those pointing backwards, so that I can just cancel out the unwanted poles. So for example, for C3 example, I have something like this. Then these two both point to the same atom here, but actually there is an arrow pointing backwards, so I have two arrows going this way, so it will actually give me a double pole. But eventually I want to have a single pole, just like in the JQ residue, because there is one color pointing backwards. So this is like the rough idea of this crystal, and it's as a representation of the algebra. But then we might ask, like, what is the algebra for the toric Calabi-Yau fourfolds?
Sorry, before that, so what is the physics of this algebra?
Oh, it's basically because you have this crystal which they label the BPS states, and then this serves as the representation of this algebra.
But what's the interpretation of these operators?
These are, if you like, these are kind of like the Chevalier generators, really, like if you have a Lie algebra. So this is like sort of like.
I mean, do they correspond to physical operators?
Well, from this picture, it's just like it's kind of like taking you from one fixed point to another fixed point, because it's like Ross Adam, like if you start from one BPS state to another BPS state. Yeah, basically that's the basically that's the direct meaning of that. These are like operators.
So you are saying that physical meaning is not clear at this moment, basically.
Well, it's just from this thing here. I don't see any other physical meanings, but there might be other connections, but I cannot really think of it off the top of my head. Yeah, but just from things here, it's basically that's all it means. Right, so for fourfolds, a very natural way to sort of guess an algebra is like, okay, because there are 5, something like this, which is like a product, something like this, but now I have Fermis. So a natural way, a very natural guess would be that I add, because these Fermis are kind of like relations, so I would just add something like this for the Fermis as well, for all the Fermis in AB. Maybe I just write down the. Well, it looks very nice, and indeed, we can write down the algebra relations, and if I call this, I call this lambda AB, and I'll just still call this phi AB, this phi tilde. Then in the algebra relation, these two are not changed. And here, this EF supercommutative would become EAFB, something like minus lambda AB Z minus W FB EA. Well, it looks very nice, but somehow this does not give me the algebra that really acts on the crystal like this. And also for F. Well, if actually I don't know how, like, if there is a sort of proof to see like this always, this doesn't work for any cases, but if we just check, for example, the C4 case, whose periodic quiver looks like this, which is a cube. Of course, there are some arrows and Fermis like this. But so if we just think of this, so here I have 4 directions. Maybe let's just call 1, 2, epsilon 1, 2, 3, 4. So suppose I just wrote the crystal in the first 3 directions. So I would have some configuration looks like this, which is actually should be the same as the plane partition. But of course I have a fourth direction, so the algebra should be different. But then everything's fine if I just wrote something like this, and this, and this, and also I can have this here, and this here. But then, for this atom, this thing here, I don't have the pole if I just keep writing this kind of expression for this capital psi. And in the end, it turns out I don't have a pole like this here, which means if I consider the action of this thing, which is something like the residue of psi, then minus this atom, then I don't have this thing here. Because I don't have the pole here, so this thing is missing. So there are different attempts to sort of to solve this problem. So in the recent paper by Galohoff and Lee, they have this expression. They were saying like, okay, let's replace this expression here, or not just replace, but let's improve this expression. So I would have something. So and they actually proved that this is the correct sort of expression as for C4. At each configuration, I always have the correct poles to give me the atoms that I can remove and I can add. So I'm not gonna write down the explicit expression, but I have something like this, where this is some factor. We should have when every time we encounter a configuration like this, and this is some factor when every time we have a row of atoms like this. So the problem for this function is that it's always state dependent. In other words, if I consider like EA acting on this C, like C1, and say EA acting on C2, they would always, or maybe they should have B. Then how I get these relations is actually I just put them together. So I have EA, EB acting some relation, some crystal, and then I have EB, EA acting on some crystal, and then I just compare their coefficients. But now, because this is state dependent, so for different C's, the things here, they are different. So we actually don't have this kind of algebra structure. And there are other sort of like possible directions is that, one way is that because in the threefold case we have like quiver on like 2 dimensions. So these are like relations and these are like relations, and these are like the poles that grow the atoms. And here I have like because it's like if we think of the brain bricks, it's like a 3D configuration. The quiver is also 3D, so I should not only have like the poles or like and the relations. There might also be like relations of these relations. So basically, for example, C4, I might have for this cube, I might also have some extra terms in the denominator. So it's roughly speaking, it's something like this. If you consider these mathematicians would like define the DT invariants for fourfolds. These are the chiros and these are the Fermis, and I actually have some the so-called obstructions to the obstructions, and they might give us some relations of the relations that give in the denominator. And indeed, we do have something in for the j and e terms. There's something like this, but still, I don't know how to incorporate this into this function. And yeah, I guess I should stop here. Thank you.
Questions?
So is the last graph the toric diagram for the fourfold? I mean, the box.
This one? Yeah. Yes. So this is I remember. Yes, this is very hard. I can. Yes, it's very hard to draw this. So this is the C4. It's like.
Okay, that's the quiver.
Yeah. So it's. Yeah, because I was saying like this is like the one-dimensional, the crystal is like the one-dimensional uplift of the quiver. So I was saying like okay, maybe I just draw the crystal in these three directions and forget about the fourth direction. So this is actually sort of like also a crystal for this case. But then already in this case I would have a problem.
So for more complicated toric fourfold, you can just glue this C4 together.
Actually, yes. So you can also glue these like sort of C4 vertices together, but that's not the approach of the crystal here. Because for crystal, actually we need is like the quiver information, and then we just get the crystals. But for the gluing process, there are also some papers discussing this kind of gluing to obtain your BPS invariants, but so far it's not clear how they are related. I mean, for three-folds, you also have this kind of like sublogical strings, and you glue them together. This is actually something very similar. But even for this gluing, as far as I know, there are two different ways to formulate this sort of vertex formalism to glue things together. And at first glance, they don't seem, even these two formalisms don't look like the same thing. And so that's not its relation to this here. But for some examples, people have checked, like they do give the same expression, like the partition functions. So they should have some connections, but yeah, it's still not clear.
Yeah, another question that you have now, we have 3 omega different times for this C4. So that's right.
You mean this, right?
Yeah.
Yeah.
But for I mean, gluing cases would be, I would say, I don't know.
Well, it's still that many parameters. Yeah. But then it's sort of like you have plane part. So because each C4 is a solid partition, and you put them together, then you have to agree for this sort of like asymptotics. So you have like 4 like plane partitions, and also you need like I guess some 6 like partitions to glue them together.
So this algebra is known for non-toric cases?
Actually,
in principle, it looks like you only need some quiver with relations.
Exactly.
So I don't see why you need toric for that.
One reason, so I tend to guess the answer is yes. So because we can also cook up the algebras for the non-toric cases, like even for, I mean, actually there is also a paper like discussing, like saying, claiming that this algebra works for any quivers as long as you have a quiver. But
Relations.
relation, I mean this thing.
No. I mean, you have a quiver, but you also will have relations.
Yes. Actually, in that paper, the claim isn't that even you don't have relations, you can also have the algebra. But it's a bit, I would say it's a bit too brave.
It's suspicious. Yeah.
And it's recorded, like, yeah, I shouldn't say this. Anyway, yes. Well, actually, we're checking this. I spent some time to write down these like expressions for the JQ residues, etc. Because I'm hoping that we can get this thing from the JK residues because they look very similar. These are poles here, and in the JK residues I have the poles there. So in principle, I should get this algebra from the JK residue expressions, but roughly speaking, because JK residues like tells me like how I grow the crystals because I have the poles. So in some sense, it only gives me the E generator because it like grows, but I don't have F. If I want to write down a sort of like symmetric thing for F, it's a bit hard. So I'm expecting some slightly different relations, but with some manipulations for the coefficients, I can actually get this thing here. But then, if you evaluate the JK residue for some non-torus cases, so for example, for I don't know, like a very typical example for torus cases, this quiver, which is like the generalized conical, which is A type. But then I have, for example, D type. Then I would not have. Okay, no, I would not have three of them. I would not have. Well, I mean, epsilon 1 plus epsilon 2 is 0%. So I would not have one free parameter, and then I would have double poles.
Yeah, sure.
Yes. So because your like covectors, it's not like projective. I think.
Yeah.
So, but then you can have some ways to kind of.
There is some way.
Yeah. You can also evaluate it, but then But then, if we want to find this algebra for whether this does like give the actual crystal or whatever representation, then we still need to check this, and I'm hoping that we can use this JK residue to check. But yeah, of course, the algebra itself is well defined. I mean, if we forget this, and it has some nice properties.
I see.
Any other questions? If not, let's thank Jack again.